Chapter 1 Introduction. Objectives. After completing this chapter, the reader will be able to understand the importance of manufacturing for the mankind, know the different types of manufacturing processes, evaluate the feasibility of a process by carrying out break-even analysis. 1.1 Manufacturing Processes. The benefits of civilization, which we enjoy today, are essentially due to the improved quality of products available to us. The improvement in the quality of the goods can be achieved with proper design that takes into consideration the functional requirement and its manufacturing aspects. The design process that would take proper care of the manufacturing process as well would be the ideal one. This would ensure a better product is being made available at an economical cost. Manufacturing involved in turning raw materials to finished products is to be used for same purpose. In the present age there have been increasing demands on the product performance by way of desirable exotic properties such as resistance to high temperature, higher operating speed, and extra load. These in turn would require a variety of new materials and its associated processing. Also, demanding working conditions that are desired in the modern industrial operations make large demands on the manufacturing industry. Further, the economics of the manufacturing operations is a very important consideration. To be viable in the modern environment, a product has to be competitively priced besides having the functional and aesthetic appeal. Therefore, it is necessary for an engineer to give a proper thought to various aspects of manufacturing. Manufacturing processes is a very fundamental subject since it is of interest not only to mechanical engineers but also to those from practically every discipline of engineering. It is so because engineering as a whole is meant for providing various materials for human consumption. For various products such as plant machinery required for chemical, civil, electrical, electronic, textile, etc., the manufacturing process forms a vital ingredient. A detailed understanding of the manufacturing processes is thus essential for every engineer. This helps them appreciate the capabilities, advantages, and also the limitations of the various manufacturing processes. This in turn helps in the proper design of any product required by them. Firstly, they would be able to assess the manufacturing feasibility of their designs. Secondly, they may also find out that there is more than one process available for manufacturing a particular product. Keeping this in mind, they can make a proper choice of the process, which would require the lowest manufacturing cost, and would deliver the product of 1.2 Manufacturing Technology, Foundry, Forming and Welding. Desired quality. This may result in slight modification in their design to suit the particular manufacturing process they choose. Manufacturing, as defined by Merriam-Webster Online Dictionary, is to make into a product suitable to use. Manufacturing remained as a craft from the first industrial revolution till the end of 18th century, with low volumes and single-piece production. It required highly skilled craftsmen to individually produce the pieces and fit them when the assembly was required. This was a slow and expensive process, but in the absence of any machine, that was the only thing possible. The availability of steam engine and the coal-fired furnaces have made the invention of a number of steam-power-driven machinery to greatly increase the manufacturing capacity. A large number of inventions related to machine tools have taken place during this period and continued into the 19th century. Towards the end of 19th century, with the invention of electricity and better engineering materials, manufacturing operations became more productive. The developments in the automobiles at the beginning of the 20th century are instrumental in the growth of a variety of manufacturing methods and practices. There are a large number of processes available for manufacture to the engineer. These processes can be broadly classified into 4 categories: A. Casting processes, B. Forming processes, C. Fabrication processes, D. Material removal processes. 1.1.1 Casting processes. Processes. Casting is also one of the oldest known manufacturing processes. These are the only processes where liquid metal is used. It requires preparation of a cavity usually in a refractory material to resemble closely the final object to be made. Molten metal is poured into this refractory mold cavity and is allowed to solidify. The object after solidification is removed from the mold. Casting processes are universally used for manufacture of a wide variety of products. The principal process among these is sand casting, where sand is used as the refractory material. The process is equally suitable for the production of a very small batch, as well as on a very large scale. Some of the other casting processes for specialized needs are as follows: shell mold casting, precision investment casting, plaster mold casting, permanent mold casting, die casting, centrifugal casting. 1.1.2 Forming processes. These are solid-state manufacturing processes involving minimum amount of material wastage and faster production. In a forming process, metal may be heated to a temperature which is slightly below the solid dust temperature, and then a large force is applied such that the material flows and takes the desired shape. The desired shape is controlled by means of a set of tools called dies, which may be completely or partially closed during manufacturing. These processes are normally used for large-scale production rates. These are generally economical and in many cases improve the mechanical properties too. Introduction 1.3. Some of the metal forming processes are as follows: rolling, drop forging, press forging, upset forging, extrusion, wire drawing, sheet metal operations. 1.1.3 Fabrication processes. These are secondary manufacturing processes where the starting raw materials are processed by any of the previous manufacturing processes described. It essentially involves joining pieces either permanently or temporarily to perform the necessary function. The joining can be achieved by either or both of heat and pressure and/or a joining material. Many of the steel structural constructions we see are first rolled, and then joined together by a fabrication process. Some of the processes of interest in this category are as follows: gas welding, electric arc welding, electric resistance welding, thermite welding, cold welding, brazing, soldering. 1.1.4 Material removal processes. These are also the secondary manufacturing processes, where the additional unwanted material is removed in form of chips from the blank material by a harder tool to obtain the final desired shape. Material removal is normally the most expensive manufacturing process, because more energy is consumed, and also a lot of waste material is generated in the process. Still, this is widely used because it delivers very good dimensional accuracy and good surface finish. It also generates accurate contours. Material removal processes are also called machining processes. Various processes in this category are as follows: turning, drilling, shaping, and planing, milling, grinding, broaching, sawing. All these manufacturing processes have been continuously developed to obtain better products at a reduced cost. Development of computers and their effect on the manufacturing processes has been of particular interest. The arrival of computers has made a remarkable difference to most of the above manufacturing processes. They have contributed greatly to both automation and designing of the process. 1.4 Manufacturing technology, foundry, forming and welding. 1.2 Break-even analysis. An important responsibility of the engineer is to choose a manufacturing process which makes the required quality of a product to the specifications and at the lowest cost possible. To fulfill both the conditions, one would have to do a break-even analysis of the various processes suitable for the production of the given object. In the break-even analysis, two types of costs are considered. A. Fixed cost relates to the initial investment on the equipment and tools required for the process. This cost would be constant and does not vary with quantity produced. B. Variable cost, on the other hand, varies with the actual number of objects made. This takes into account the raw material required, energy consumed, labor cost, cost of special toolings, cost of tools used, and other administrative overheads. These requirements are directly proportional to the quantity produced. The total cost of manufacture is thus the sum of both fixed cost and variable cost. This may be written in equation form as TC equals FC plus VC n Q, where TC equals total cost, FC equals fixed cost, VC equals variable cost per piece, Q equals production quantity. The same is shown in graphical form in Fig. 1.1. Normally, as the quantity of production increases, the cost per unit produced decreases. This is due to the fact that the fixed cost associated with the production remains constant. Total cost, cost, variable cost, fixed cost. Production quantity. Figure 1.1 Typical cost curves. If an engineer has to make a choice between two different processes for manufacturing the same component, he or she may first estimate the fixed costs and variable costs for both the processes, and then plot the total cost curves for both as in Figure 1.2. The point where both these curves intersect is called the break-even point. It implies that the first process will be economical if the quantity of production is less than that of the break-even point, that while beyond it the second process is economical. Introduction 1.5. Cost. TC1, TC2. VC1. VC2, FC2. FC1. Production process 1, economical process 2, economical. Quantity. Figure 1.2 Break-even curve. The break-even quantity N can also be obtained by equating the total costs in both the processes. That is FC1 plus N yen VC1 equals FC2 plus N yen VC2. N equals FC VC VC2 112. This would give a positive value when fixed cost of a process is greater and variable cost lesser than those of the second. If both fixed and variable costs are lower than the other process, then the latter process is always uneconomical whatever may be the production quantity. Another way of plotting a cost comparison curve is to calculate the average cost of production for different production quantity. The average cost is given by total cost production quantity. Average cost per piece. Closed die forging. Open die forging. 10-100, 1000, 27. Figure 1.3 Break-even chart. 1.6 Manufacturing technology, foundry, forming and welding. A typical curve is presented in Fig. 1.3. Alternatively, a base cost for one process could be taken, and the curves could be plotted as in Fig. 1.4 for the relative cost per piece versus production quantity. The relative cost can be defined as the cost of the component in relation to any convenient cost, such that the abscissa would be represented by more convenient units that are easier to comprehend, such as those shown in Fig. 1.4. 1.20. 1.15. 1.10. 300. 1.05. 1.00. Relative cost per piece. 2000. Green shell mold. 0. The manufacturing of a component may involve more than one process, or more variants of the same process. In the first case, it is necessary to consider the costs of all the processes, while computing the total cost for each of the processes. Example 1.1. In the manufacture of a machine fitting involving drop forging and machining, there are two options available. First option is to produce a blocker type forging followed by heavy machining, or a close tolerance forging followed by finish machining. The costs are as follows. Blocker type, close tolerance, forging die cost, setup cost, forging piece cost. 33,500 to 500 160. 6500. 86 247 121 600. 10,000 80 200. Find the economical manufacturing method for production. Introduction 1.7. Variable costs are Locker type. Open die. Questions. 1.1 Explain why the multiple choice questions. 1.1 Break-even analysis classifies the various costs as A. Fixed costs and indirect costs, B. Fixed costs and variable costs, C. Variable costs and indirect costs, D. Variable costs and direct costs. 1.2 For a typical manufacturing operation, the variable cost may include the following costs: A. Cost of the die, B. Tooling cost, C. Part material cost, D. Setup cost. 1.3 For a typical manufacturing operation, the fixed cost may include the following costs: A. Overhead cost, B. Tooling cost, C. Part material cost, D. Running cost. Answers to MCQs. 1.1 B, 1.2 C, 1.3 B. CHAPTER. 2 Engineering materials. OBJECT.